Hello and welcome back. This will be the third and final video on section 1.2, and we'll finish this section by looking at different kinds of equations and their solution sets. So the first type of equation is called an identity, and what makes this an identity is the fact that it is always true. So an example of an identity is something like x is equal to x. Well, clearly every number is equal to itself, so x is equal to x. And that doesn't matter what x is. 1 is equal to 1, 2 is equal to 2, 3 is equal to 3, 4 is equal to 4, and so on and so forth. So it doesn't matter what x is. This equation is always true, so it's an identity. The next equation doesn't even have an x in it. 3 is equal to 3. But since there's no x in it, it doesn't matter what x is. X could be 0, it could be negative 10, it could be 13 and a half, it could be any number. 3 is equal to 3, and this is always true. The last equation that I have written here is again maybe a little bit more complicated, but if we simplify both sides, we will eventually see that this is an identity. This is something that I want to point out that it's not always clear what is an identity and what isn't until you simplify it. When you simplify it, you make it something that looks like either of these two things. So if every single number is a solution, there are two ways to write down the solution set. The maybe more explicit way is to write this down as a set. And we can say that the solution set is the set of every single x. That's a number. So x is a number. So this is saying that everything is a solution as long as it's a number. That's everything. Another way of writing this down, the set of all real numbers can be written with a blackboard bold R. I believe that the roster notation on the left is what the online homework assignments use. This is the notation that I was taught, and this is actually what I prefer because it's shorter and easier to write down. So the next kind of equation is one that's not always true, but it's still sometimes true, and this is called conditional. So whether or not the statement is true depends on what the value of x. So it's conditional on the value of x. So in order for it to be conditional, it has to be true for at least one value, but it can't be true all the time. So it has to be true sometimes and not true others. So this first example is a fairly clear. I need that to be equation. The first example is one that's pretty clear. This is true if x is equal to 7, but if x is equal to 4, it's not true. So it's at least true for one value and it's false for another value. And it's clear that here there's only one solution. This is only true when x is equal to 7. It's not true for anything else. This next equation, we can see, okay, this will be true when x is 2, but it's not true when x is 100. 100 squared is certainly not 4. This has more than one solution, though. This has two solutions, when x is 2 or when x is a negative 2. So this is an example of an equation that has more than one solution, but not infinitely many. This last equation, again, it's not clear that this has a solution, that there are multiple solutions, but this is again something that if you were to simplify this and work things out, you would also find that this has two solutions. So the solution sets for conditional will depend. So it depends on what it is. So for example, for this first one, we know that the solution set it's just going to be the number 7. However, for the next one, we know that 2 and negative 2 are the solutions here. So if I write down 2 and negative 2 and put those in a set, so you can have a solution set with one thing in it, two things in it, hundreds, if not thousands, if not infinitely many. But if it's everything, you're an identity and not a conditional. The last situation is when the equation is never true, and this is called being inconsistent. And an example If I were to say 1 is equal to 2, well, that's simply false. So this is never true. If x is 1, 1 is still not equal to 2. If x is negative 13 halves, 1 is still not equal to 2. So this is simply never true. It's the same with this one. If I said x is equal to x plus 7, no number is equal to itself plus 7, 7 more than it. 10 is not equal to 17, 20 is not equal to 27, 33 isn't equal to 40. This is never going to be true. So this is an inconsistent statement here. So the solution set is going to be the empty set. There are no solutions. Again, one way to write that down is to write down our curly brackets with nothing in there. It's empty. Or the more common solution that you'll see in the homework is going to be a circle with a line through it, meaning there are no solutions. The solution set is empty. So let's look at a couple of examples. This first example, again, these will be fairly simple. We need to simplify this. So on the right-hand side, I'll need to distribute. So we'll have 4x minus 4 plus 3. And then when I simplify this a little bit more, we'll have 4x minus 4 and plus 3 is negative 1. Here, I can say that this solution set is going to be empty, and this is going to be an inconsistent equation, because the left and the right-hand side look nearly identical, but they've changed just a little bit. So let me show you how I know this. I am going to get rid of the 4x by subtracting 4x on both sides. What happens when I subtract 4x? Those will cancel, and those will cancel, and I'm left with minus 7 is equal to minus 1. So this is inconsistent. And then the solution set is empty, because negative 7 is never equal to negative 1. Here's another example. We've got 7x plus 9 is equal to this mess. Let's simplify it, and we'll know exactly how big our solution set is going to be. So we'll distribute 9x plus 9 minus 2x, and I can consolidate the 9x and the minus 2x. Kind of looks like a y. So this will be 7x plus 9. And right here, I can look, I've got the same thing on both sides. 7x plus y is always equal to 7x plus y. It's the same number. So this is, in fact, an identity. And the solution set is going to be the set of all real numbers. If you didn't notice this right away, you might continue on simplifying, but that's okay. For instance, maybe I want to subtract 9 from both sides. And those guys will cancel, these guys will cancel, and I'll get 7x is equal to 7x. And then I can subtract 7x from both sides. And those guys will cancel, these guys will cancel, and we're left with 0 is equal to 0. So I recognized that it's an identity up here, but maybe you simplify it a little bit more and you get 0 is equal to 0. This is a lot easier to recognize that this is an identity. Both work. This last one is maybe the most tricky. We're looking at this and we see 2x is equal to x. And one reaction that you might have, and this is certainly a reaction that I would think is pretty valid. I want to simplify this. So maybe one way I can simplify this is dividing both sides by x. So after I divide both sides by x, what'll happen? The x's cancel over there, and we'll get 2, and then x divided by x is equal to 1. Oh, but 2 is never equal to 1. So the question is this inconsistent? And the answer is no. I divided both sides by x, but I'm not allowed to divide by x if x were equal to 0. So what if x equals 0? Then 2 times 0 is equal to 0. Hey, that's true. So when you divide by x, you have to be careful. You must always ask yourself, what if x were equal to 0? So another way to go about this, if I was given this question, one that I could see that this is a solution right away, instead of dividing by x, I'm going to subtract x from both sides. So when I subtract x from this side, 2x minus x is just x. On the right-hand side, x minus x is 0. Oh, hey, look, there's my solution. So dividing by an expression can be dangerous. What if that expression were 0? And you always have to go back and check. Did I get rid of any solutions? You have to check if instead of dividing by 0, those happen to be solutions. My fix here avoided that because I didn't divide by something that could be 0. I just didn't divide at all. And I will stop there. Please, guys, if you have questions, reach out to me. I'm here. I'm available for all sorts of questions. Email me. Stop by my office. I have office hours. I can meet outside of office hours. So I just want to reassure you that I'm here and I'm available to ask questions for help.